All right. Hello, everyone. Welcome to another PIBBSS speaker series. Today we have with us Daniel Polany, professor of artificial intelligence at University of Hertfordshire. I hope I pronounced that close to correct. In the United Kingdom. His interest is the modeling of cognition through the lens of information theory, and his goal is to use the latter to identify a route to understand the principles of emergence of intelligent cognition throughout evolution without the requirement of an external guide. Today, you'll be talking about information and its flow. Bit of housekeeping. You can ask questions by raising your hand, and then I'll allow you to talk. Or you can use the Q&A function at the bottom to ask questions. You can also thumbs up them or comment on your or other people's questions. And we'll be answering them as we go. For now, we may change our mind. All right, Daniel, take it away.
Thank you very much. And just to make sure, if there's Q&A, am I supposed to check it out, or
no? I will kind of raise my hand and tell you that there's questions. Don't worry, I'll keep an eye on for that.
Excellent. Okay, thank you very much. It is a pleasure to be here. Well, here, virtually here, at the West Coast, I think. So I can tell you I would like to be at the West Coast right now. The weather must be nice. In any case, Hertfordshire was pretty well pronounced. It's actually easy to remember if you just remember to sneeze. Hertfordshire. So that's kind of the pronunciation, more or less. And as Dusan, right?
That is correct, yes.
Yeah, Dusan said, I'm going to talk about information, and I'm basically interested in information in the sense of Shannon and variants thereof, and especially in the flow of information through the environment and through agents, because we believe, basically my group works on the belief that understanding cognition, we try to build artificial intelligence, but we put a lot of effort into that, but we know evolution has been able to create intelligence out of from scratch in a way. The question is, why is it possible? If you don't want to assume, of course, intelligent design. And the question is, what are the conditions for that? And the hypothesis, the working hypothesis that we have is information is the currency that matters in this context. So let me dive into it, and we'll develop the tools as we go. So first of all, I would like to say that much of the things that I'm talking about has been developed over the years with a huge amount of people. And you see that is like Nihat, Nathaniel Berger, Malte Harder, Tali Tishby, Alexander Klubin, Hippolyte Chavin, Nicola Catenacci-Volpi, Christoph Salge, and many, many, many other people. So this is not a one person's work. It is a work of a whole community. And I would like to thank them. So I feel that the slide, unfortunately, they are all very small, but each of them has contributed substantially to this work. So the size is reflecting the size of the community, not the size of the contribution. Okay, so also I would like to thank a number of sponsors, amongst them 3 European Union sponsors. Fortunately, we can now again get, we're part again of the European family to some extent. After Brexit, it was not so clear. So let's thank them. Then I will announce that there will be a research fellowship and PhDs in the Adaptive Systems group that will probably be advertised in March, April. We also currently have a PhD studentship advertised for a topic on sustainability measures using information theory. They're very closely related to empowerment. It's in conjunction with my good friend and colleague Jan Kim, who's a computational systems biologist. And so that is currently open. So if you're interested in that, please contact me or forward the message to somebody else. And I'm happy to send you the contact. Okay, so much for the shameless plug. My apologies for that, but this is interested people are people who know best, who might be interested in this type of research. Okay, let's dive in. So Oscar Wilde, famously one of the most prolific creator of mottos, or as we would say today, memes, said it is a very sad thing that nowadays there is so little useless information. I think that statement is now truer than ever, which is quite foresightful in any case. And information is what we're going to talk about, and information that's useful versus useless is one thing that we are going to consider. So the model. Let's dive into the model, and the model we are going to consider, because we're talking about Shannon information, we need to talk about probabilities and how they are basically used to compute information. So let's consider a world. This is a world W, but W is a random variable and it's indexed by time. Here's t minus 3, here's the world at t minus 2, t minus 1. So you see there's this discrete time. And if you see this chain here, this is a Markov chain effectively. So the world contains everything that you can possibly know or need to possibly know to predict W t minus 2. There's of course a random transition. So this arrow indicates a conditional transition, W t minus 2 given W t minus 3. This is kind of what this arrow represents. And so this is a Markov chain, which you can also read now as a Bayesian network. In fact, I want to invite you to read this as a causal Bayesian network, which means that there is also semantics, that if we intervene in a node here, if we modify the distribution somehow, that modification affects the nodes downstream. So now we are modifying this world into a world that is being affected by an agent. What is an agent here? An agent is a very simple thing, something that has an action. Again, that is a random variable, and that random variable, together with a world that took, say, time t minus 3, that world time t minus 3 and the action at time t minus 3 together create a world at time t minus 2. So W t minus 2 given W t minus 3 and A t minus 3 is what happens next. So what happens in this time step depends on first on what was there in the time step before, but also on the action taken by the agent. Now the agent, as you see, is blind, so it does not see anything in the world. It also doesn't have a memory. So to be consistent, the right way to do that, we have to make the assumption that all these arrows are the same. So in other words, the distribution of these actions is the same, and also the effect of these arrows on the world is the same. Any change of effect we want to be incorporated actually in the W in a way, because the agent itself cannot have memory. So that all these distributions are exactly the same. And you can see that as if there's a distribution A, that same distribution all over the way, basically the world dynamics is now parameterized by the distribution of actions. So the world is now essentially has a dynamics, and that dynamics can be parameterized by this distribution of actions. That's how you can see this agent. It is a blind agent. We call that an open loop agent. Even a blind agent can do a lot. So for example, you can have agents that just bump around and do stuff. And they push, for example, things that you put in the ground towards the walls. So there's this nice experiment where robots without any control, without any sensory input, just push around and shift things to the wall just by following this one policy. Now we increase the model. We introduce a generically sensing agent. So the agent now is able to take in the world. So here there's no dedicated sensor. So we don't specify what the agent is allowed to see. So in other words, the action A now depends also on the world of that time step. In some way, this dependency, as we don't have memory yet, should be the same in every time step. So it's time homogeneous. But now we are actually allowed to look at the world. In fact, because we have no constraint on this arrow, it means as in principle, we could look at anything in the world we want to. We could also look at the whole world. The A action might depend on very detailed little aspects of the world. Generally, that doesn't make sense. We'll see later why not, but in principle it could. And I think there's a question
there. Yes, Mateus asks, are you assuming this is deterministic for now?
No, absolutely not. It is stochastic. These are stochastic kernels. These are stochastic kernels. Okay, so everything here is probabilistic. And you want it to be probabilistic. That's intentional. Because we will talk about trend and information. And probability is actually the world in which this information is going to live. Thank you for the question.
Awesome.
And finally, I'm expanding the world. Not finally, it's not the last step yet. I'm expanding the world to include sensors. So what's the difference now? The sensor is limited. It's a particular form of how you can take in information from the world. You cannot see everything. You can see only light in the visible spectrum. You can see only X-rays. You can only listen to sound. And the sensor is a limitation, a structure on the information you are allowed to take from the world. Of course, an organism is limited in what it can take, so the sensor is usually determined by the evolutionary process. Again, this is all time homogeneous because there's still no memory here. And finally, the complete form of the model is that. By the way, do you see my mouse?
Yes.
Okay, very good. I just want to make sure that you can follow it. So here, this is the most complete model for this discrete time step. There's a world. The world impinges on the sensor. The sensor now does not inflict on the actuator directly, but goes through the memory. The memory itself is driven by what happened before. So now the agent has a memory, the agent has a sensing, and the action depends on both. And this is a very nice model, the representation. Is a very nice one because it highlights multiple symmetries. One is, of course, the symmetry past and future. Of course, there's the directionality of the arrows, but essentially it looks very similar. Sensing and acting are almost dual to each other, right? They look almost like the dual version of each other. And the second thing to look at is that there's another symmetry along this axis. If you look at the axis between separating the agent and the world, you see that actually there's no big difference between memory and world. They almost look the same. And I keep joking, actually, that the choice of the world, the letter W, is because when you mirror it along these axes, the letter W is just a mirror of M. So the interesting part about that, structurally, basically world and the internal and the external world are almost the same. What's the difference? Well, the difference is semantics, because you see, the memory is, of course, our brain, for example, and the brain keeps a very compressed picture of the world. While if you look at the world is physics, and physics is relatively simple. I mean, it's not simple, but it's much, much simpler than biology. So in physics, you throw a stone, it's very easy to predict what it's going to do. Easy to predict means it's very compressible what the object does. It means the world is highly compressible. It has a low information density, while memory in general is highly compressed. So the only way to distinguish inside and outside of an agent, if you look at this diagram, you can't see a difference. The only way to distinguish them is to ask what's informational density in the world versus the one in the memory. Now you ask me what's the definition of that? Well, we don't have a good definition of that yet. It's more an intuition, but I want you to just keep this intuition in mind to understand that the duality between world and agent is very, very far, it reaches very, very far, and breaks only once you actually talk about the information content itself. And I notice 2 questions, which I'll try to answer. Okay, yes, there were just comments. Very good. Now, we move on, and I want to talk very briefly about relevant information. What is relevant information? Relevant information is a term that today basically it's encompassed in the bigger topic of so-called bounded rationality, where people say, I want to make a rational decision, but my resources are not arbitrary. I have limited resources, And if you have limited resources, you cannot do full rationality. So you make a trade-off between how much resources you have and how rational you can be. And typically the resources are expressed in terms of information. Now, in more specific context, we talk about relevant information as that information that an agent needs to achieve a certain utility. So if you have a utility defined, say you have here a world, again, our agent with memory, there's a reward, and you think of a reinforcement learning agent, doesn't have to be very complicated, just a reinforcement learning agent that accumulates utility. You can, of course, be optimal, but you can ask, well, for optimality, I have to distinguish so and so many states. I have to transfer that much information from my sensor to the actuators to make the best decision. And I say, I do not have that capacity. I have only, instead of 2 bits of decision capacity, I have only 1 bit. The question is, what should this 1 bit actually pick out to achieve the highest possible utility? This is what we call the relevant information. The same thing also for the optimum case. Again, we don't ask for everything. We ask only for the bits that we need to get to the optimal utility. And so in a way, that is what we would call a pull information. It's how much information you have to pull from the sensors to inject into the actuators to make my decision. This is the relevant information. You see these 2 arrows here. This pi is the policy. The policy basically extracts information from the sensors and pushes in the actuators. Now the question is, what do you extract? So for example, if I'm a football player, basically my relevant information is, where is the ball? And maybe where are my teammates? That's all. I don't care where the audience is in the end, right? It doesn't matter, because for the football player, it matters. That's where the ball is. That's where my fellow players are, and my opponents, of course, right? But nothing else actually matters. There could be even less relevant information. For example, if you play a video game, and at the beginning, video games have lots of graphics and so on, but once you play a game a lot, turns out that the graphics is not important. You only care about what can you do, what weaponry you have, and that's why often these very simple video games work very well, very immersive, because the main story does not depend on the vagaries of particular graphics. So this is a pull information. And I forget for a second for the memory transmission over time. I basically now look just as the instantaneous relevant information. Doesn't have to be, but here we do that. So it's a pull information. However, remember that I talked about the fact that the diagram is actually symmetric. Input, so down and up, there is a symmetry, a horizontal symmetry. So this begs the question whether I can ask the dual question. So if there's pull information, is there push information, and what does it mean? So the push information has a name. I'm sure you know it by now. So it's not really a cliffhanger. I can't make a cliffhanger out of that. But the push information is the information that you push through your actions into the world and recapture through the sensors. Okay, let me reiterate that. So how much can you actually inject into the world in terms of information and recapture? What can you do to the world, in fact, that you can see the effect of? Now, the relevant information is a minimization. You want the relevant information to be low. You don't want to have to make difficult decisions because information processing is costly. This is the idea of relevant information. Relevant information basically says, give me the least amount of information I need to make a good decision. The push information is the opposite. You want to be able to push as much information as possible. It's a potential that you don't do, you want just to find out how much it is you can do, okay? And this is a quantity that can be quantified. I'll do that in a second. But I first want to highlight the fact that there's pull information, relevant information, there's push information, which is its dual, which plays very nicely with the symmetry of the perception action loop diagram that we are looking at. So Why do I spend so much time on this information here, information there? Because you see, one thing that information does, and that is a relatively recent discovery. I mean, Ashby had that already in the 50s, basically the core idea, but it was very informally stated. And he stated that you can't formulate a law of information, namely, if you want to absorb variety in your environment. You have an agent, an organism, or controller that needs to absorb variety in the environment, and you need to make it go away because you want to stabilize your environment. Then you need variety in what you can do and what you can pick up. This statement has been extended and sharpened by Hugo Touchet and Seth Lloyd. And this is actually a very interesting study because what they showed is, first of all, I make the statement, then I interpret it for you. So let's assume you have an open loop controller. What is an open loop controller? An open loop controller is an agent that does not have sensors. So it's our first agent that just parameterizes the dynamics of the world. So if you have an open loop controller, that open loop controller, let's assume you pick the best you can choose. The best you can choose is here very simply defined by the one that in one step, so coming from a stationary world WT minus 1, in one step can reduce the entropy of that world. Remember, the world is a random variable, so it has an entropy, can reduce that entropy as much as possible. So think of it like, how much can your mama clean up your room when it's messy? So you have a messy room and you give her one time step. How much entropy can she reduce? Say 10 bits, right? She reduces it by 10 bits. It's a lot in one step, but let's assume you can do that. That's the best an open loop controller can do without looking. So basically the agent doesn't look, does something, and this is the best reduction you can get. By the way, reduction might be negative. There's no expectation that it's positive, but I just for sake of intuition, let's assume it's positive. If you have this reduction for the best open loop controller, then the following theorem holds. Once you close the loop, so the controller, the agent is allowed to look at the environment, then what the agent, the closed loop controller can do, delta H closed, that's the entropy reduction of the closed loop controller that is able to look at the world. That controller can not reduce the entropy by more than the open loop controller can, plus whatever the agent takes in as sensoric information. So information of the action about the world. In other words, we have an upper bound on how much better a closed loop controller can be than the open loop controller, and that bound is determined by the information that the action can have about the world. And this is a bound. There's no guarantee that you will achieve it. Dusan, yes.
Just to read out the two questions that came in. From Vojta Kovarik, we have, could you give an example of push information? I have a vague sense of empowerment, quote unquote, but I'm not sure if that's the same thing as you mean.
Yes, it's empowerment, and I'm going to talk about empowerment in more detail later.
All right.
If you permit me to postpone that response, I hope I will be able to give you examples for that.
All right. And from Stavros Anagno, I hope I got that fairly correct. Could you say that based on this Bayesian causal network framework way of looking at things, that information about the world is encoded implicitly in its agent's action?
That is a very interesting question. I really like this question. There is the statement, people talk about the fact that in a way our brains and what we do and what we memorize reflects the world around us. So yes, to some extent, some aspects of the world are encoded in the actions. In fact, we actually have looked at digested information. This is not something I'm talking about here, But digested information was a concept introduced by Christoph Sager and myself about what actions reveal about the world when you observe the actions of an agent, of another agent especially, what they reveal about the world. So when we talk about relevant information is the mutual information between the relevant actions that actually achieve a utility, and the state of the world or state of the agent. And this information is, of course, symmetric, right? Information is symmetric, it does not have a direction. So by very nature, the actions do reveal something about the world. The point is that in the digested information framework, what we said is, okay, looking at what other agents do tells us something about the world. And the second point is, because agents are intelligent and they extract interesting information or relevant information, as we say, this information is typically more valuable or more dense than random information in the world. That's why when animals are in the jungle and there's lots of stuff going on, most of the stuff is irrelevant. But then there are warning signals by birds or warning signals by other animals that the predator is arriving, for example. And then animals really listen, they pay attention to that. Because this information is much more valuable when it comes from other agents than if it's a random rustling of the wind. An agent does something, sometimes it's irrelevant, right? If a bird sings in front of my window, that's nice, but it's not really information generally. But what another agent does, or for example, when you run after people because you're hungry and you see these people and they very clearly are looking for a place to eat, and you run after them and find. Actually, that's how we found a nice bar in Edinburgh once. We were looking for a place, and then my friend said, "Oh, let's just follow these girls. They know where they're going." And I said, "What? Why? We are not going to stalk them." And he said, "No. They know where they're going." And we followed them, and then it was right. He was absolutely right. We had no idea where to go, but we observed their actions. So Stavros, to give your answer, yes, the action does encode information about the world, and often much more valuable information than just random when you pick it random.
Awesome. We have Mateos asking, is it correct to say that in order to minimize entropy in expectation, a closed loop controller needs to take the action that maximizes mutual information between the action and the observed inferred world?
Not necessarily. As I said, it's an upper bound. You might be very unlucky and just get the wrong information. Or there is no relevant information that improves your entropy. So you may waste a lot of brain power for essentially nothing. You may want to talk about, I want to maximize capacity that I can do, but then we are actually entering into empowerment territory, which is essentially about capacity maximization, but with respect to the environment. Okay, so it's an interesting question, but I think by just maximizing your mutual information between the action and the inferred world may or may not be the thing you want. That is not, it's not obvious. It's not obvious. It's a good question, but it's not obvious.
All right. And from Nora, something that seems really interesting in this context is the relationship between actions containing information about the world and actions containing information about the agent's goal. If the latter also applies, this poses the question where this latter boundary condition comes from or where it lives.
Okay. This is really a tricky question. So let me just separate two aspects. Okay, first aspect is yes, the action is not the pure information. It's pure information about the world, and it's information about the goal. Completely right. Now we know from studying information decomposition, those who do this field, and I actually always recommend to PhD students not to do this field unless you know what you're doing, because essentially there are so many suggestions of how to do that. There are like, I don't know how many, 20, 30, 40, I don't know how many variants of that exist. It's very clear that there is not a single measure of decomposition on which everybody agrees. For me, that is a signal that we either don't understand the field or the field is not manageable, or we have to classify what's there. So the first question is, can we separate them? I would say in first order of approximation, no. So separating the influence of the state and separating the influence of the goal, I don't think that the separation is very, very easy to do. You can, of course, apply the information decomposition of your choice on that and work with this. That's an option. So I think in terms of decomposition, they are probably not that separate. I suspect that there's a mixture of separate input and things that are not separate. So I'll give you an example. If you have a geometry, so you have a world, a navigational world, and your goal is getting somewhere. So your actions tell you something where you're going, and it also tells you something about how the world is structured. And this is not entirely separate, right? Because to be able to talk about where you're going, you need a structure in the world, right? If the world is a Euclidean space, then you only have a pointer, and that's all you need to know about where the goal is, a pointer, direction, length, okay? But that makes a lot of assumptions about the world. If the world is a maze, that's clearly not enough. You have a whole complicated script that you have to follow to get to the goal. So you see how that information is it's not obvious what the information is and where it is and who contributes what. The Euclidean structure is much nicer because what it allows you to do is actually separate out much of what the world does, how the world looks, and your action. So your action is a direction and a distance. Thank you very much. That's all you need to know. And that's what the Euclidean symmetries essentially do for you. So it's a very deep question. I'm just starting to probe it. The question whether the letter boundary condition comes from. Okay. Now there's another way you can look at it, and that is something that I can say something about, and that's goal relevant information. You can say if there's a goal is like a condition that you want to achieve, and that can come from some choice of goals. So for example, when I play a quiz game, like 20 questions or something, the goal is one word out of a dictionary, for example. Yeah, and you have 20 questions to answer that. So I think of a weird word, for example, it's ziziva or something. Ziziva is a word that is I think a crazy animal. And it's famous because I think it was used to win some world championship in Scrabble or something. And okay, you have to find that. That is very clear, right? That's where it comes from. So from that point of view, your goal can just pop up randomly, and you just assume that's the first time it appears. And the third one is the most interesting one, in my opinion, apart from and that is the biological emergence of a goal. I don't think personally, that's my personal opinion, okay, people may disagree. I don't believe, evolutionarily, I don't believe in goals. I don't think that there is anything like a goal in evolution. So it's rather what survives in a way, whatever that is. And goals are just convenient ways for us to talk about intermediate stages that are very well defined with a very narrow channel that allows us to forget everything that happened before. So the concept of goal or task in evolution, I would say, is simply talking about something that masks or screens the past. So when I say the goal of this player is to win the game, so that once the player won the game, I don't actually care about the game. It's not really true if you're interested in the game, if you're a chess player or something, but the reality is they won. I don't care about anything else. You forget about the history, and this was your goal, and the goal is basically well-defined small set of states. So I gave you 3 answers. I don't know which one, if at all, answered your question, Laura. Feel free to ask an additional question.
Sure. Yeah, Nora says, no, this was great. Mateusz adds, I think this kind of goal non-realism is locally valid, but using the same criteria, we could say that nothing exists except quarks or something.
I think it's not that saying that goals don't exist as a practical concept. What I'm saying is goals don't exist as an evolutionary concept. They are basically a convenient way of talking about informational, I don't want, or kind of a historical bottleneck where information is being concentrated. So the way, it's a longer story. I think we would have to actually sit at the table and show some diagrams, because it's not something I'm talking about. But the way I like to look at it is a goal is a way to compress history in a way. So I don't actually care how we got there. And so it's emerging. So it's not like it doesn't exist, but it's not actually a priori. It emerges. It's probably a better way to say it. I apologize for saying it doesn't exist. It's not the right word.
All good. Yeah, Mateusz says it will be fun to sit at the table. Nathaniel asked the question, but as it's a bit more general question about sharing information, maybe we can save it for the Q&A at the end. And for now, just continue with the talk. I'll again raise my hand for next round of questions.
Shall I answer Nathaniel's or shall
I think we keep it for the Q&A at the end, before people forget the first half.
Okay, I will follow your lead. Anyway, so the closed loop controller has this constraint. So you have a limit of how much entropy can be reduced if you have closed loop as compared to open loop, and that's upper bounded. What is important about this? It is a statement about information. It does not talk about physics. It does not talk about energy. It does not talk about anything. It is nevertheless a hard constraint on information. You can make essentially, this is not conservation law, this is an upper bound law, but it's a law of information about agency. In other words, you have something like the conservation, or it's like entropic laws or things like that. And in fact, in some cases, you can actually say this is the amount of information you need to achieve a goal. So I want to just to highlight, information can be treated almost like a conservation quantity in some cases. That means that independently of whether you have physical laws or anything, cognitive laws do follow certain constraints on how much information you can process, how much information you need to achieve certain things. And if you don't achieve that, then essentially you basically can't do, basically there's no perpetual mobile of such kind. So there's no perpetual mobility of first kind, which means you can't generate energy out of nothing. There's no perpetual mobility of second kind, which means you can't generate work out of temperature difference, basically constant temperature baths. And in a way, there's no perpetual mobility of third kind, which means you cannot generate information out of nothing. In decision making, you need the information, a certain type of information that's defined by the task that you are handling. Okay, now there's a nice statement by Bruce Lee. I think this is a very inspirational quote. A goal is not always meant to be reached. It often serves simply as something to aim at. I really like that, because it makes clear that essentially what matters is your action, right? Goals are a concept, an imagination, and a linguistic thing, or a picture in your mind, but they don't have to be real. What's real is your action. And now I'm coming to universal utilities, or as they are called these days, intrinsic motivations. So a little bit of motivation, and much of this work, and I don't have time here in this relatively short lecture. It's not that short, but I don't have time to really go to the details of everything that led me to this considerations. But one motive that I'm very strongly driven by is to understand how intelligence arrives in nature. And if you look at nature, the problem with nature is really that life evolves, and it doesn't have to, but it can get more complex, and it gets significantly more complex. And in fact, you can get humans, or rather, it's not the point of the humans, but essentially introspective animals that are able to solve complex cognitive tasks, very, very complex cognitive tasks, far beyond their own lifetime, far beyond the lifetime of possibly even their own species. And the question is how do we get there? And so much of my thinking has been driven by the fact there must be something in evolution that guides evolution to this point. And if you don't want to make either extremely arbitrary assumptions or random search or something, and you don't, on one hand, and on the other hand, intelligent design is not for you, then you have to ask, okay, what is it that is a currency that moves me into the right spot? And as I say, I mean, this should not come as a surprise, given that I'm the speaker here. I believe information is a very good candidate for one of these possible quantities. And here is an example for a way you can work it out. So if you look at biology, the success criterion is survival. Survive. And you as an individual, or as your germline, your species, survival is all that matters in biology. And as I said already, the concept of a task and of reward is not really sharp. So these are things that we introduce to make it clear how to evaluate things. And if you're in academia, you know there's all these counting papers, counting this, counting that. But really, what is actually the goal of research, or the goal of certain things, or goal of life? Some people, I mean, if you look at money is actually good measurement for some people. But still, the task and the reward are not sharp concepts. And what's worse, in biology, the search space is very sparse and very large. Yeah, this is one of the big problems that a pure random searcher would have to solve. So if we take pure Darwinism, or as I like to say, naive Darwinism, by the way, Darwin himself was not naive, right? He actually understood the problem, the magnitude of the problem. But if you look at pure Darwinism, you get feedback by death. So you do stuff, you get born, you do stuff, and then if you die before you have offspring, fail. The example I give is that you have a course, you take a BSc program, and you study, but you never get feedback. You study, do stuff, learn, blah, blah, blah. Then there's final exam, you fail, out. It's very clear that's not very helpful for learning, right? So in other words, the flow from the feedback from the selection process into what is feasible is a very, very, very sparse, and it's not very good. And so this is a big dilemma for naive Darwinists. So the question is, how can we overcome that? Well, biologists will say, well, you have homeostasis, that dense networks that guide living beings away from dangerous states, for example. Hunger and thirst are very built-in systems, but there are so many situations in our life, there can't be a homeostasis for everything. And what's worse, homeostatic mechanisms are very organism-specific. What does it mean, organism-specific? Organism-specific means that you essentially have, for example, you have the naked moles. The naked moles live underground. They can handle much higher levels of CO2 than other mammals can, because they live underground, so they have to be able to cope with elevated levels of CO2, of carbon dioxide. There are other things where organisms can handle better cold, or they can handle one thing better than another, can handle low temperatures. There are humans that can, for example, live in very high altitudes. There's a tribe in, I think, Indonesia, not Philippines, Indonesia, I think. This tribe actually lives by diving for pearls and things like that. And they have a mutation that permits them to stay underwater 15 minutes or so, which is for a non-tribe member, this is basically about the maximum, in the region of the maximum that, for example, highly trained apnea divers can do. I think 22 minutes is something like the maximum, and they don't move and don't do anything. These guys dive down, get the pearls, and get up again. So they have a completely different makeup of their storage of oxygen. It seems to be stored in their spleen. Now, what it means that the homeostatic mechanisms are organism specific. When you have artificial agents, you have to individually design them. You build a humanoid robot. The humanoid robot has different legs, has different sizes. What is the balancing right? So, question is, what is a better way to do that? Something that is evolutionary successful must work generically, right? It may fail occasionally, but it should work generically. It should generally work. The fact that it does means that this suggests a more fundamental principle. And the idea is essentially that there are universal drives and utilities which do not depend on the organism. They depend only on generic things, right? These drives are essentially of the same nature, except that that they may be applied in different organisms with different constraints, but the drives are the same. The core idea is that adaptational feedback that tells an organism this is a good thing to do, this is a bad thing to do, should be dense and rich. What does it mean, dense and rich? So dense means you get it all the time, not just at the end of the run. Okay, feedback you get only at the end is very problematic. As I said, you study, fail. Feedback by death. That is not dense. That's very sparse, not very informative. So you can't correct yourself. You have to memorize everything you've done, and then you have to trace back what may have gone wrong and so on. This is very expensive, very difficult to do. That's one reason why chess, for example, is such a challenge, because essentially when you play chess and you have no coach, you have to think, at which point did the game go wrong, for example? Then you have to remember the whole game. You have to remember what went wrong. You have to evaluate the alternatives. Very, very expensive. So dense. The other thing, it should be also rich. What does it mean, rich? So if you play the game hot, cold, you look for an object, the object is hidden in the room, then you say hot, 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 warm, warm, hot, hot, cold, cold. Now you give dense feedback, but it's not rich. You basically, your feedback is quite uninformative, right? It's you have if you have something like hot, warm, cool, cold, you have 4 different statements. So that's 2 bits of information at best. That's not rich. Okay, rich means there it is. You point to the object and say there it is. That is much, much more rich information, because the finger basically picks out the direction. There's only one spot where it lands. It's expected from social convention that this spot is really uniquely then identified by whatever you look at when you follow the line of the hand. So that would be a rich feedback. And this, of course, has started people to be interested in since the 2000s, artificial curiosity learning process, automatic principle, intrinsic reward. One exception, of course, notably is Jürgen Schmidhuber, who has actually seen the importance of the topic already in '91. Okay, so he actually, I think, introduced the concept of intrinsic motivation, I think, as that term, if I'm correctly informed. Of course, there are specifically information theoretical versions of that, free energy and predictive information, which is essentially information theoretic version of the homeokinetic principle. That a very, very clever principle introduced by Ralph Thayer in 1991. I think the bigger paper is 2001. And basically the principle is you try to generate movement that keeps the predictiveness high. So you do things that allow you to predict the future better, but to be actually relevant, you want to take movements that have an unstable future, so that actually have something to predict. So if I enter a dark room where I can't see anything, of course I can predict what I will see next, namely nothing. But this is not very interesting. There's nothing to predict. So if you maximize predictive information, or you do the full-fledged homeokinetic principle, you're looking for predictions that are non-trivial. You try to be as predictive as possible in a world that has actually much of a richness in which to predict stuff. And there's an approach that is actually very related to what we're going to talk about later, namely empowerment, and that is called the causal entropic forcing, and that was motivated by physical principles. I think probably the maximum entropy production principle. That latter principle does not really work, unfortunately, it turns out. There have been attempts to salvage it with England's theorem. However, it seems like the idea is actually quite interesting, namely thinking of that a physical system tries to enter states in which the cone of future trajectories has the highest entropy it can reach. So this is basically causal entropic forcing is very closely related to empowerment, but the physical principles behind it are not guaranteed and not well established. The empowerment, which I'm going to talk about now, is explicitly motivated by evolution. So we do not claim at this stage there are physical principles behind it. It would be very nice to, if it was be possible to say that though. So we have that following ansatz. The ansatz is the following. You say, if you have an evolutionary system, the evolutionary systems are economic. They do not want to waste resources. I think one of the questions is actually related to that. I'll be happy to discuss that later. But essentially, evolutionary systems don't want to waste resources. This means if I have a sensor that picks up stuff I cannot change, I don't need this sensor. Vice versa, if I have actions that do things where I don't see the effect of them, and therefore cannot make use of them, that doesn't count either. So I want that my actuators the actuations match what I can sense the best way possible. I want, in a way, an impedance match for information of my action perception loop outside of the agent. I want the actions to do things that actually are relevant to things I'm picking up. And I want to do them only these things. This is what I want to maximize. If I'm not maximizing that, that means that either evolutionarily I can reduce my sensors or I should increase my actuators. If I'm an organism that already has these actuators and sensors, then I want to move into the niche I've evolved for, namely that's a niche where this matches best. So I'm trying always to move into this niche. This is kind of the postulate that we're taking. And here I give you an example. So for example, you have cavefish. Cavefish live in dark caves, and in these caves there's no light, therefore the eyes are useless. And so these cavefish actually de-evolve the eyes. The eyes degenerate and they don't see anything and they only hear. So when they're sloshing around, they can feel, hear. Well, they use the line organ, which indicates what they can pick up and smell and things like that. However, same type of environment, different solution. Fish in the sea, in the deep sea, also, it's very dark. How do they solve it? Well, they actually don't de-evolve their eyes. They evolve the actuators. They can create light. The light is created by microorganisms, but that's not what matters. What matters is the fact that now these fish have actuators that create light, that make the eyes actually useful. In other words, here you see two possible solutions to the same question. You either reduce your sensor to match the limited actuation, or you increase your actuator to match the more powerful sensor. And let's formulate it a little bit more technically. We maximize the potential to inject information into the environment via the actuators and to recapture that information from the environment via the sensors. This is the ansatz we are taking. Or in a simpler motto, in the language of Tobias Jung, one of my former postdocs, I thought he had it boiled down to a very pithy statement. He usually made very pithy statements, was very good at that. He says, being in control of one's destiny is good. And you should know about it. So the whole point is that you're not just in control of your destiny, you need to know about it. If you can't see it, it doesn't count. Okay? And this is what empowerment is measuring. Empowerment is the potential to control your destiny in a way that you actually can pick up. We can also find a link to control theory, a very natural link, in fact. Essentially, it's an information theoretic version of combining controllability, being control of destiny, with observability and knowing about it. So it's not a one-way road. Control and you can observe that control. In fact, this is ending up with a Hankel matrix by which you can actually compute this type of control. So what's the formalism? Let's be a bit more technical. Up to now, it was motivation. And the technical part is the following. So we have our agents again, world, sensor, memory, actuator, and so on. Let's get rid of the memory. Now this is a reflex arc. World impinges on the sensor, you quicken action. It has an effect on the world. Let's forget the link between sensor and action, because right now what we're going to look at is what I will call free will actions. Free will actions are basically actions that drop down from the sky magically. And this is what we're going to look at. So the first action is random distribution. And this random distribution has a causal effect. Remember, we talked about causal Bayesian networks. So in other words, I can intervene in the node, and this intervention spreads throughout the network. So I intervene in this node, it impinges on the world in that time step, and now time passes. The effect that I had on the world is propagated to the next time step, and now I intervene again. These two actions, although I don't have a connection, please think of a connection. There is a connection between them. They can be correlated. It is perfectly okay for this action to somehow be correlated with this one. That's perfectly fine. I wait another step. Time passes. And again, I pick an action, and again, this action may be correlated with them. So these are not independent ones. We will soon write the missing node. But first, I want you to just concentrate on what we're doing. First action, second action, third action, and say after three observations, three actions. This is just a random choice of three. I'm observing the effect. So I do one thing, I do another thing, I do a third thing, and then what happened? It's a bit like these kids standing in front of the wall, throwing stones until they hear glass break, right? They do stuff until there's an effect. But here the time is fixed. So I do 1, 2, 3, and observe the effect. And now these are random variables. And I can now ask, okay, what's the mutual information between these three random variables and the observed effect as it passed through the world? And I can maximize this. So I can maximize how much information comes from the three random variables to the observed sensor. These are the variables, and this is a sensor. And this is a quantity which I call empowerment. I maximize over all the distribution of these actuations. Now, if you observe closely, you will realize, of course, that this depends on the state I started in. So it depends on the state. So empowerment is not just one quantity, unless I marginalize, but I don't want to do that. It actually depends on where I am. So in this state, I can look at this maximization and I get a value in terms of bits. So in the state, empowerment has a certain value. I write the notation a bit more compactly, so the action sequence is just as a boldface A. This is the effect of my action sequence onto the sensor in this state, and I maximize that. This is a potential. It's not what I'm doing. It's only the empowerment of the state. It's how many things I can do in this state. I think there's a question that might be related to that. Probably we should take that. There's still others. Okay, I think some of the other questions is probably best answered at the end. But if there's any question about empowerment, I'm happy to answer it now. Okay.
Yeah, I think nothing about empowerment in particular.
Okay. Good. Okay. So because for clarification, it's perfectly fine to ask to respond now. So first of all, a couple of properties about empowerment. Empowerment is a function of state only. So it depends only on the state. It does not depend on anything else. If you're in a state, it has an empowerment. It can be zero. Zero means you can't do anything, right? The world just happens as it happens. You have no influence over it, or you can't see the influence at all. It is a pseudo-utility, so you can treat it in first approximation as if it's a utility, okay? Why pseudo? Because strictly spoken, you're not really allowed to average over it. A utility has a property that is a so-called certainty equivalence property. Never mind what that is. It means basically that utilities, if you average over utilities, you have different outcomes, you have different utilities, you average over them, then the utility of the average outcome is the same as the average of the utilities. This is not correct for empowerment, but in approximation, you can pretend it is, right? And let's put it this way. If you want to not think too much about that, that's how you can use it in first approximation, okay? The second thing is it's defined by the world dynamics only. You do not need a reward. So I have a world dynamics, do not need a reward, and I do get an empowerment value. It means that I can actually produce a utility for a world without having an external engineer, evolutionary process learner, critic, having to learn that utility. It is local. You have seen that empowerment, we said 1, 2, 3 steps. You can do 5 steps, you can do 10 steps, but you start from where you are, a limited number of steps. That means it's local. It's not, you don't need to propagate values back all the way through the Markov system, to the MDP. And you don't need a reward function, as I mentioned. Let me summarize again. It is information controllability, observability, as we said, the informational efficiency of the sensory motor niche. Basically, if that niche is not very efficient, you can actually cut out actuators or sensors, or try to move into a niche where it's better, or grow them to make it better. Another interpretation of empowerment is empowerment means that you are in states that maximize your ability to choose distinguishable futures. It means that you can choose a future in one or the other way that you can actually distinguish. And the assumption, of course, is that if you can choose your futures, you can choose more futures, you have more options to ensure your survival. So the idea is that high empowerment is kind of an approximation or heuristic that makes you flee from death. Death is empowerment zero. So low empowerment is very similar to death in some extent, and you don't like that. You want, as an organism, you want to be away from its viability in a way. So there are other interpretations which are very natural to understand. I know that empowerment is slightly a concept that people need to get used to a bit, but actually it's quite natural once you understand. So for example, in games, you have mobility. I'm in a state and I have a choice of moves. And if I can create a lot of successive positions, reach a lot of successive positions, that's high mobility. It's very close to empowerment. Yes, Dushan.
Question from Nathaniel. How can an agent receive this pseudo utility? How would it know its empowerment?
Very good question. So the way to compute it normally is, say you need a model. So because it is potential, you need a model. It's not given to you. In most of the scenarios we actually compute it because we have world knowledge or God's eye view. But in general, there's nothing essential about that. You can make it completely epistemic. So if you have an epistemic model of the world and it's wrong, doesn't matter. Then this is what you think your empowerment is. If you have a Bayesian model, for example, of your future steps. Let's make a very simple example. So you have a move forward. You have two choices. One gets you left, one gets you right, but you don't know what they do. And so you have a Bayesian model of what they do, and the Bayesian model is completely equal. So I take one action or the other action, basically I can't see a difference. In the epistemic model, your empowerment is zero, subjectively. If you can distinguish, it goes up. Some people also consider that empowerment, therefore, as curiosity. It's not directly curiosity. It doesn't actually care about novelty, but it cares about novelty that makes a difference. And so in the moment you have an even slight difference between the two outcomes, then empowerment might actually try to explore that and try to find more and more distinguishable states. So you need a predictor. And the epistemic uncertainty of that is perfectly part of the empowerment formalism. It's perfectly okay to use it.
All right, thank you. Nathaniel says, got it, makes sense, thanks. And Clem asks, do organisms good heart empowerment, for instance, by increasing the resolution over some subspace they have good control of to increase their empowerment?
What does good heart mean?
Maximize for a certain measurable thing that serves as a proxy for a different thing. So we want actually, I don't know, maximally happy lives, but we measure it as GDP. So we end up maximizing GDP regardless of happiness.
You could also run into self-fulfilling prophecy or actually into traps. Yes, and that can happen. And that does happen even in nature, right? So you can have an over-optimization for the wrong thing. For example, if you look at sexual selection, which is one example that Darwin, that shows how smart Darwin was. He understood that random search would be too slow. So he actually, commandeered the organisms to help in the search by sexual selection. And so in sexual selection, you can actually start to distinguishing things that are completely irrelevant to your survival. Songbirds is a classic example. The complexity of the song is partly very, very hard. And it's so hard that songbirds, at least some songbirds, do actually degenerate their singing area after breeding season. So the singing area in the brain grows for breeding season after it is being decommissioned. So yes, you could actually have empowerment evolve towards more resolution. And if there's time, I have actually an example for that.
All right, thank you. All right, let's continue for now.
Okay, so another classic is, of course, money. Money and empowerment. If I want to explain empowerment in 5 words to somebody that is not a scientist, I say, well, money. Think of money. Money is nothing except potential, right? Money is potential work or potential goodies, right? Money means I can do things, and now just to see the difference. It can be spent and can be invested, and with empowerment it's exactly the same. So say you have a little money, so £1. If you have £1, then you can spend it on chewing gum, or spend it on, I don't know, something else, but there's not much you can do with that. Now if you have £1 million, then you can either spend it on a big party for everyone, having good fun, or you can invest it in the banks, and then the bankers can have a big party. Yes, I know I had done this joke also in New Orleans, but the point is, the money gives you a lot of options if you have more of it, and doesn't mean that you expended it. Yeah, you can keep it, try to increase it, or you can spend it at once and it's gone. Exactly with empowerment, that's the same thing. So empowerment is a potential that you may exchange for value on one go, or may invest into getting more empowerment over the time. So the relation to money, the similarity to money is actually quite striking. One example for exchanging value is a football team. A football team controlling the ball, that controls the ball well. Think of Pep Guardiola's style. He likes to control the ball. He likes his team to be in control of the ball, empowerment. But when the player is in front of the opponent's goal, that's not longer what you want. What you want is to get that ball into the goal. And that is, you basically take empowerment as like a voucher and put it in, and instead you get the goal. And you essentially exchange it for something else that you need more, that's of evolutionary advantage. Now, Tom Anthony and Christoph Salge once corrected me and told me, well, Daniel, actually it's still empowerment, because when you get a goal, what happens, you're more likely to win the game. When you win the game, you have more money, you can continue playing, you can continue in the league and so on. Yes. So if you really want to spin this further and further and further, it's possible to do so. But I basically use goals here as simplification of my life, simplification of an argument. If we cut off our consideration when the goal is reached, like winning the game, then still empowerment can be used to make the goal happen, to exchange things for the goal. Another term that is really interesting in context of empowerment is affordance. What is affordance? Affordance, okay, there's stuff happening around you, and there are certain things that are easier to do. This bottle here, I can grab this bottle, and it's easier to grab in the middle because it has this way of holding it. So affordance is something that makes it easier for the organism to do certain things, and that can be because it's intentional, or it can just have emerged by random chance. Or your embodiment adapts to make sure that the environment creates an affordance for it. So if you're a fish, you have flippers, then essentially affordance means the water affords your flippers with the right movement. If you try to walk with flippers on your feet on solid ground, you will find that is not a very good affordance. Then there's a concept coming from psychology, Österreich, perceivably different outcomes, or efficiency divergence, which already was formulated in 1979. It was not information theoretically, it was just about the fact that the outcomes are there, but it's very clearly related concept. And the psychologists, and we have chosen the word empowerment specifically from sociology, namely the ability to change your environment and knowing about it. So the term actually is the sociological term that we had in mind. Graph centrality, of course, we're central in the graph. And finally, probably one of my favorite interpretations, that is Seligman and Meyer, antithesis to helplessness. So if you have learned helplessness, it means you learn that no matter what you do, all the outcomes will be the same. This is the opposite. So empowerment is saying, yes, I can change the world. Yes, and I know that I can. Dushan, yes.
Sebastian asks, you mentioned that zero empowerment is a state of death, and that empowerment is therefore a quantification of viability. There could be many resources over the state of model that are zero at death besides empowerment. Can you motivate the connection between empowerment and viability such that it's stronger than, for example, mutual information of one's sensory input?
Okay, I should say something like that. Empowerment zero doesn't mean necessarily death. You could imagine that you're trapped, and because empowerment is local, your empowerment is zero, you're not dead, right? But death, the argument goes only one way, right? If you're dead, your empowerment is zero. Empowerment is zero doesn't mean you are dead. Okay, so number one. But it's not a nice state to be in. And we had one article where we looked at the 3 laws of robotics. And one of the problems that Isaac Asimov had was that, well, if you want to protect as a robot, you want to protect humans, you put them in a golden cage and goodbye, thank you very much. The humans are safe. That's clearly not what humans want. They don't want to be in a cage, they want to run around. So essentially we ended up recasting the purpose of the 3 laws into empowerment language, in cross-empowerment language between agents, between robots and humans. And that then becomes much more nicer, because then the robot wants to increase empowerment of the human. So he will never put him in a cage. He wants to make sure that the human is safe, so not dead, but still has all the options, right? So increasing empowerment is exactly what you want. as a first law. And if you're interested in this question, I can suggest that you can read this paper. It's in Frontiers on Computational Intelligence, I think. If you're interested in that, I can give you the link. Because we actually argue with the same spirit of Isaac Asimov, but several of the problems actually disappear, conceptually at least. And pragmatically, we have some indications that it might work. Okay, so we have some simulation that might work. Anyway, so I don't know whether I answered Sebastian's questions properly. Did I, or?
I think so, but Sebastian can ask follow-up questions.
Okay. I will be happy to answer. I think I'll try to move on so that we actually can have a discussion. I already over an hour.
No, it's okay because of the questions. It's fine.
Okay, so helplessness is basically the opposite of empowerment. You want empowerment as an antithesis to that, and I think that is a way to interpret this psychological. So the psychological term was actually the one we were thinking of when we gave the name to it, but turns out that there's a lot of things that links together. Now, one way to look at empowerment is also a bit different, right? Think strategic. So one character I always has is like, tactics is what you do when you have a plan. Strategy is what you do when you do not. And that's why politicians always talk about strategy. So empowerment is about strategy. If you know what you want to do, if you have a goal, and now I'm talking about a goal in the naive sense and the naive machine learning or AI sense, I have a clear goal, I want to do that, no problem. I plan, I think, I play chess, I try to predict what's going to happen and so on. But sometimes you're in a situation where it's very unclear. I don't know where I am, I don't know what will happen, this can happen, this can happen. The world is far too complicated to predict everything, right? So people always think chess is not a good model for the real world in a way, because it's far too plannable. And so what is a strategy then? Strategy is you position yourself in a way that you have a response to as many things that could happen as possible. And that is, in a way, empowerment. Empowerment positions you in states, or maximizing empowerment positions you in states that have as many responses as possible, in expectation that at least some of these responses will be useful for you. It increases the chance that responses are more likely to be useful. It's not a guarantee, of course, it never is, especially since empowerment is local. But it's kind of a bet that states with higher set of options have a better chance of finding a response. So let's start with a simple example. I talked a lot, but at some point you have to look at how it looks like. So box pushing. Box pushing is the following. We have a box. This is a grid world. This grid world, I think it has 11 times 11 sets. I have, or no, it's actually infinite. It doesn't really matter. I have an agent, and the agent is going to do 5-step empowerment. So what it's going to do, it has 4 actions. So north, east, south, west. I'm not sure if it can stop. I forgot whether it can stop. Probably it can stop, but it really doesn't matter. Let's say it can stop. So it has 4 directions plus 1 stop action. It can then live in this world. In this world, there's a box, and we are going to consider 2 scenarios. The box is stationary, so it cannot be moved. And the second parameter of the scenario is whether the agent can see the box or not. So the agent can see itself, but may or may not see the box. So we have 4 combinations. So let's look at the first case. Box is invisible to the agent, the box is stationary. And then we see that the agent, when it's far away from the box, dark values are high empowerment values. They're roughly empowerment 6. 6 is basically the logarithm of 61. The binary logarithm. 61 are how many fields you can reach in 5 steps. So you took 5 steps, you can reach 61 fields. And because the movement of the agent is deterministic in this case, you basically can compute empowerment simply by the entropy of the uniform distribution over the reachable states. That is log to 61, which is roughly 6 bits. This is the value of this dark area. When you approach the box, it turns out that the empowerment is reduced. The box is invisible, but it will block your movement. As you come to the box, there are certain movements you cannot make. Therefore, as you come close to the box, the empowerment goes down. And you see that it's worse actually in these corridors, because this is a grid world, these corridors around the box. When you're on the box, however, then the program runs like that. You can actually hop down from the box and then do whatever you want to do, and then turns out then you have again all the 61 possibilities that you may want to choose. Okay, so this is the stationary box, and box is invisible. Now let's make the box visible to the agent, and turns out it's exactly the same, because the fact that you see the box doesn't change anything. The box is just there, it's fixed. So think of the sensor as a cross product between observation where the box is and where the agent is. This cross product is essentially trivially extended. So basically there's a position of the agent, the position of the box, but the position of the box never changes. Therefore, stationary box and visible box has no difference to invisible box. Now, we'll move to the pushable box and invisible. When the box is pushable, the agent has no touch sensor, so only vision sensor, only it sees only itself and can move the box, and therefore every spot here has 6 bits of empowerment. Every single spot has, from every single spot you can reach 61 locations. This is completely evenly distributed environment, right? This has a good empowerment, but the empowerment landscape doesn't tell you much because everything is the same. Finally, the most interesting case is when the box is visible and pushable. Now, what we have is that the agent, when it's far out, it has 6 bits. So what is white now is actually 6 bits. So what was black here, but it's a rescale here. So what the white area is actually the low value of here. We have 6 bits of freedom when we are far from the box. When we're closer to the box, then the box can also be moved. So I can move myself as I like, but I can also move the box. So I have 2 things I can change in these 5 steps. And the best I can do is actually, when I'm on the box, I have essentially almost 7 bits of empowerment. It means I have almost 2 bits more close to the box as I have far from it. So there's an incentive, an automatic incentive for me as an agent to be close to the box. In other words, a box as a manipulable object is attracting the agent in terms of empowerment. This was also our original motivation when we came up with the quantity, is actually how do we make robot go to the ball, agent go to the ball in a football game, basically RoboCup. We have a RoboCup activity. We didn't want to give a reward. We didn't want to tell the robot, come closer to the ball. You get a reward when you go closer, or you get a reward when you move the ball. We didn't want to do that explicitly, and we wondered, is there something generic we can do? And that's actually the origin of the idea, but we needed the Boolean random network, the Bayesian network formalism to be able to write that down properly. Okay, so this is the first example. And here is a more sophisticated example. Here we have a pendulum. You can do it with single pendulum, but I'll show you with a two-link pendulum, which is more difficult. At that time, this was pretty much state of the art. At that time, reinforcement learning had a big problem getting a double pendulum up. Double pendulum means you have an acrobat hanging down from the rod and having one engine in their hip to swing up. And basically, this was so difficult at that time that essentially when you swung up, people were saying, okay, the reinforcement learning was successful if the feet get high enough. They didn't even demand balancing. And the solution that balanced made an artificial switch to LQR control. So basically properly designed controller at the top. So we did try this with bang-bang control. So you have momentum to one direction, momentum impulse to the other direction with empowerment maximization. So you do that movement that gets you into the highest empowerment successor state. And turns out that it almost balances it. The last bit was achieved. That was an ingenious idea by PIBBSS, who said, well, let's just add LQR control to the toolbox that empowerment may use as an action. So there's bang, bang, so bang left, bang right, and LQR. And empowerment can choose which one it wants. And it automatically switches to LQR. So it's a little bit of help, but essentially it's empowerment that decides when the help is actually invoked, which I think it's fair because it actually chooses it when it's close enough, not before. So here is the demonstration. Just a second, this is a bit slow here because this is all, yeah, no. Okay. I hope you can see that.
Yes, we can see.
So it looks like it swings up. That balances it. And essentially the LQR is invoked only at the end because the bang bang is too rough to actually do that. Okay, so this is an example how empowerment is very good with balancing. And note, there's no external reward. We just say maximize empowerment. So this is another one. This is kind of fun. It's a little bit hypnotic. I'm wondering, I have to explain a bit more. I can do it later when we do the discussion if you're interested. I think I would move on with other questions first, with other slides first. So here is a scenario that is actually a kind of Minecraft type style. The movements, the actions are all deterministic, but the space is quite big, so we explore it stochastically. So we create forward rollouts and compute how many states are being reached and take the logarithms of that. And because everything is deterministic, the dynamics is deterministic, the empowerment can be estimated as log of the reached states. It's a lower bound to the real number. And if you want, it is actually regularized lower bound because through the sampling, you don't see states so easily that are difficult to reach. So let's look at the first one. The first one is a little world. Always takes a bit of time. So this is a lava world. There's this lava river, and this agent can take building blocks, move them, destroy them, transport them. And you see that I run it again. It runs, puts the building block over the river and moves somewhere else. And it basically builds a bridge of the river. Nothing special, but it's nice to see that it actually does that. The lava is actually very bad for the agent. That agent should not touch it or it will die. So here we have what I call the climate change scenario. But the climate change is a bit nastier. It's climate change on Venus. So it's lava here. We pour in the world. The poor agent, this agent is a typical politician, acts in the very last minute, builds a little island and climbs on top of it. So that was very lucky. It's still just alive. It's just about alive, right? So it has, I think, 1-2 places it can go, but it's just about alive. So that was not the best solution, but it survives. Okay, so let me show that again. Lava is being poured in, and that agent only acts in the very last minute. It's typical politician. Okay, so think of it as a. Okay, now let's take a Dutch politician here. So the Dutch, you can guess already what it's going to do. So this guy is building a ditch and a dam. Okay, and it blocks the lava and has here a little bit of degrees of freedom for its own world where it lives. Okay, so it has a ditch and a dam, and that's good enough. It's a better solution, definitely. Well done. But my favorite one is this one. So same scenario, but this agent goes underground. Okay, puts in this cork, closes up everything and starts digging underground. And that is exactly the scenario that many apocalyptic movies actually show. So we didn't tell the agent to do that. It discovered it on its own, right? This was its own discovery that creating tunnels below the lava and living underground is a solution to impossible life on the surface. Okay, so what we can say that in 85, I forgot the percentages, it was something like 80, 15, 5 or something. So 80% of the cases where this stupid politician that went on build a little island, if 15% it was the dam building agent, and then 5% of the cases discovered the solution going underground. Yeah, that's that. And okay, I have a few more extra things to say, but perhaps I can take some questions to make sure that the people don't sit on their stack, if you want.
There's a question from Stavros about the lava simulation. Is there no learning here? The agent just spontaneously does these actions by maximizing empowerment.
In the which world?
Generally in the lava simulations.
Yes, no learning. Yeah, we could include learning. There's very little work on that. There is a bit of work by Tobias Jung where we actually learn the model on the fly. I didn't show that. I do think there's a lot to do there. I do think when we include learning there, I think yes, there's lots of potential in that area. Yeah.
All right. I think the rest of the questions we will do at the end. I invite the audience to thumbs up the questions that they want to ask to make sure that we have enough time to go through your presentation, and then I'll ask the highest rated questions or something like that.
Brilliant. Okay, so here are a couple of things that I haven't shown a lot, so I hope it's interesting for you. It may be new for people even who know the talk. So this is work done by Lucas Eberding in his MSc thesis. And basically, he looked at collective empowerment. And what we looked at, one of the things that we were wondering about is, if your system is in kind of critical state, it's kind of unstable state, can individuals do things? Are they more empowered? So we modeled that as an Ising model. For those who don't know the Ising model is a very simple model of a magnetizable substance. Think of it as the following. You have an array of spins or magnets, say, that are going one direction or the other direction, and they want to align one way or the other, depending on the energy function. And essentially, what we know from physics is that, say, you cool down the system, so you reduce noise, you have no vibration, no noise, no heat bath, then these magnets, depending on how their energy is chosen, try to align themselves. Let's say, let's look at the case where they just align themselves. They try to be one, so you get with one big block of 8 aligned magnets. They all look at the same way. Now, when you heat up the system, this magnetization goes down, at some point disappears entirely. So everything becomes random. And that's a relatively sharp transition. It is a so-called phase transition at which this happens. And we know that phase transitions are a point of maximum sensitivity of the system. We were wondering what happens if you use agents that are essentially masquerading as spins, but they're not spins that they, in terms that they follow, they have their own will, and they try to manipulate the environment. What do they see? They see their neighbors, they see what their neighboring magnets do, and have a sequence of length n, and they can choose whether they go up or down. So they can turn each other as they want. They have a source of energy that allows them to do that. And because this is very difficult to compute analytically, we obtain the forward model just through simulation. So we look at the state, we simulate forward what could happen, compute the empowerment from this estimated value, and the agent decides what they do. And the empowered spin acts to maximize expected next step empowerment. So this is how it looks like. And the results are very surprising. We actually expected that the empowered spins will hijack the system and try to mess it up, make it more unstable. And the exact opposite happened. The empowered agents didn't like that at all. They wanted the system to be nice and stable and not making any phase transitions, not becoming chaotic. In fact, when you had only, I think that is really 0.10%. That means 1 per mil. So 1,000th of agents. And when you look, what was that? That is, I think this is temperature and this is magnetization. So I think this is temperature and this is magnetization. When you have empowered agents, as you increase the temperature, the magnetization goes down, but only very mildly so. If you take them out, it drops to this green curve. So these are basically curve that emerges when you stop the agents being empowered. It drops down to the normal magnetization curve. So essentially you have a phase transition. So the agents do not like the environment to be critical. I'll soon say something about that because I think it's a very important statement. If you look at the susceptibility, what's susceptibility? This is again the temperature here. Susceptibility is basically how much does the magnetization of the system depend on external influences, external magnetization or modification. And we can see when there's no agents, then around the phase transitions, it's very susceptible. The whole system can be changed very easily. In the moment you introduce 0.1%, yes, 0.1%, it's not 0.1, it's 0.1%, already drops by half. And already at 1% of agents, it was almost disappeared, the susceptibility. So the agents actually sit there in this collective and they absorb the susceptibility. They make it go away. They stabilize it. Oh, let me just move. Why is that important? I'll tell you why that's important. People talk about the fact that life at the edge of chaos. So one of the things that we are looking at, what's the origin of life and how do living organisms find where they want to be. Empowerment, if that is something that organisms actually try to maximize, and it's a hypothesis that it might be the case, right? It's not the only candidate for that, but it's a hypothesis that it may be an interesting quantity. They don't like edge of chaos if these results are actually relevant. In fact, they don't like chaos at all. They rather absorb the chaos. They rather own the chaos. They become controllers, masters of the chaos. They don't like the chaos to be around them. So organisms don't like chaos around them. They will make it go away and they will make it part of themselves if necessary, so that they can decide whether there is chaos or not. So in other words, not edge of chaos is what organisms want. It's being masters of chaos. So that's a little intermediate conclusion. And here, finally, I think this is the last thing that I'm talking about. And I just give you a highlight of that. This is relatively new. One of the criticisms of empowerment is it's very difficult to compute. Difficult in the sense it's expensive. If you if you go to the continuum, it's lots of effort to compute it. Even discrete, you have to do all the combinatorics. Especially for long time horizons, it's very expensive. And when it becomes continuous in time and space, it becomes prohibitive. The question is, can you do better? And it turns out, yes, it's possible. This is work with Stas Tjomkin, who's the first author with Ilya Nemenman and Tali Tishby. That's probably the last work that was done before he passed away. So this is basically a new approach based on controlled dynamical systems. So here's the idea. You take your dynamical system, and by the way, don't be afraid of the discretization. We will make it continuous. The discretization is only the first step to apply the algorithm, but it converges very nicely for decreasing time steps. So we take the dynamical system, discretize it in time. So here's a discretized system. So XS is the state at time, discrete time S, and basically it consists of the dynamics of the system itself. So the system left alone without control would just do this. It would take the system from XS-1 and move it to XS, but we now add a little influence. This is so-called affine control, which is basically some function of the location times linear the action picked at this current state. This is the action we picked the current state, linearly combined, added to the natural dynamics. This is the dynamics that is controlled. And we now say all the actions are small. This means we can actually work with local linearizations. The system is not linear, but locally in changes of actions, it is. And then we can show that the control effect on the outcome at the time S, independence of action modification at time R, is computed by the chain rule. Essentially, it's a chain rule, right? It's a differential chain rule. It's quite straightforward. This is just a formula. Basically, you take the derivative of the derivative of the derivative of the derivative, and you derive this thing, and this derivative basically through the chain rule, you end up with the chain of Jacobians of f through time with one multiplication of the so-called gain. This is called the gain at the time step you are in. And this gives you the change, the sensitivity of x at time s given r. It's a very simple idea. Once you have it, everything else falls out of the formalism. And now all you do is, I'll come to the matrix in a second. So all you do is you look at these different differentials. And for empowerment, we look at these. So we look at basically the sensitivity of x at time s2 given r1, r2, r1 plus 1, r1 plus 2, r1, and up to r2. So we have actions at different times from r1 to r2, and look at the sensitivity of the outcome sensitivity of that. And this gives us a matrix. I mean, there are different variants. I'll talk about them in a second. But this matrix here is going to be used as a linearization of what the variation of the actions through time is going to do to the last state. Remember, empowerment is about I do something, do something, do something, do something, and observe. And here's the same thing, right? I do something, do something, do something, do something, and observe. But I linearize that through time. That gives us this matrix here, which is this submatrix, the red submatrix. And when I multiply it by this little sequence of actions, I get a linear modification of what happens at the end. But of course, everything is noisy. And at the end, there's an observation noise. This is added here. And this gives me a change in observation at the end. When I do that, I have a linear Gaussian channel. This is a standard information theoretical quantity for which the channel capacity, which is essentially empowerment, is well known. We know how to compute it. I won't go into details. It's very easy to compute. It's standard knowledge. So in other words, we get this matrix from this Jacobians. We have this linear Gaussian channel. We get this. We can compute empowerment for very long time series. And what's nice, it converges very nicely if you make the time difference go to 0. It is very, very well behaved. No instabilities, anything. But the cool thing about this, if you look at the matrix, it's much bigger than just empowerment. There's much more there. So there's, for example, this green thing here. This green thing is very similar to causal entropic forcing, where at the beginning of the causal entropic forcing, this is the quantity we discussed earlier, the physical quantity, where you give it a kick. So you give it a kick and then just let it run and observe the states that are spread out from there. And this is essentially corresponding to the green part of the matrix. And finally, there's a blue part of the matrix. If you look at that one, that is essentially the well-known Lyapunov exponents from dynamical systems theory, but constrained to only the subspace that is controllable. So in other words, we can now see how empowerment actually fits when we look at it from the perspective of dynamical systems very neatly into existing theory of dynamical systems and with other concepts in a similar field, at least in the linear Gaussian approximation. And the cool thing about that is that when you now walk along high empowered values, what you're doing is you seek critical Lyapunov paths. You look at their paths where the controllable Lyapunov exponents are as positive as they can be, right? So as positive as can be and controllable. So to come back to my intermediate motto, you don't seek as an organism or an agent that follows empowerment as a principle of life, don't seek the edge of chaos. You don't want the edge of chaos. What you want is to become the master of chaos. And with this, I conclude my talk.
Thank you very much, Daniel. Yeah, probably claps from everyone in the audience, which we cannot hear. But let me ask questions that have gotten the most upvotes. We have approximately 13-ish minutes, although we can go a little bit over schedule if you have time. Nathaniel asks, I have a more general question about the use of Shannon information to quantify cognitive resources. Why do bits correspond to resources, like metabolic resources and such? One slightly unsatisfying explanation I can think of is that brains have communication channels to map to states to actions, and so Shannon's bounds are relevant here. But are there other more direct justifications?
You know, it's like cutting open a wound and putting salt into it, Nathaniel. Well done. Yes. Why is that? It's not that direct, and I agree with you. What we do know is that the nervous system is very expensive. We know that brains eat 20% of the metabolism in humans. Flies' eyes use 20% of the metabolism. And you can't demobilize neurons easily. Actually, you can. There are actually sea squirts swim around, and then they land on a rock. When they like the rock, they stick there, and they will never ever leave it again. And then they eat their brain. And as I'm citing a good friend of mine, it's like a tenured professor. So once they find a rock where it's comfortable to sit, they eat their brain. So yes, sometimes you can decommission your energy consumption. Most of the time you cannot. So it's better to think of it as, the way I like to think of it is actually as an information marketplace. So a brain is like an infrastructure set up, and there's a limited amount of information you can actually process. And the postulate or hypothesis is that you essentially take out from this market certain type of resource and use it, but you can't allocate it to different things at the same time. It's not necessarily translates directly into energy. That being said, actually you can calculate how much information you can process in general when you have a certain amount of ATP, for example. If you have an ATP molecule at room temperature, I think the free energy of the ATP molecule corresponds to, I think, 1.7 K bits of processing power, a single ATP molecule. So the free energy, I'm not talking about crystal free energy, I'm talking about physical free energy, corresponds to 1.7 K bits. Where are they? Why don't we see them? Well, here's my understanding of what happens. Again, this is just, you know, a very, very, very vague hypothesis. Essentially, much of what happens in our body's metabolism is just housekeeping. So much of it is just cycles that keep bad stuff out, good stuff in, and just let this organism run. And very little of that is extra that can be then left to the next level. So proteins use probably most of the ATP just for housekeeping. Then a fraction of that, perhaps a thousandth of that, goes further to the next level, and then of that, a thousandth goes to the next, and all that remains is kind of what we have free for you know, thinking and acting and doing these things. And look at your life, right? When you pay taxes and you have to house move and so on, how much do you do research, right? You can do research only if somebody else does the job for you, right? But if you have to do all these things, then, you know, much of your cognitive effort is actually housekeeping. So your question is very good. I do think that on the level of Landauer, yes, you can directly translate energy into information. On the level of cognition, it's not quite as clear. I would say much of it is just infrastructure that is available, and where I would claim that if you use the resource at one spot, it's not available for another one. We know that resources are limited, and you can actually check that out, for example, in studies of flight, how you call air traffic controllers. It's very well known how much they can handle, and they should not exceed that amount. If they exceed that amount, that's a problem. We also know, for example, that working memory is very, very limited. Working memory of humans, some people, there was a theory that it was something like 2.5 bits, it's probably less. It's very limited, it's surprisingly low. Right, we don't feel that because the brain organizes it quite well, but then you find that your capacity is actually far lower than you think it is.
Awesome. Thank you. Nathaniel says thank you as well. Nora asks, there's an idea in the AI safety discourse about whether we might be able to define boundaries of agents such that they might track, at least conservatively, something like moral patienthood, i.e. where the piercing of such a boundary is equivalent to doing harm to. I wonder whether you have thoughts on how we could formalize boundaries in a kind of dynamic way, such that it also captures something like autonomy or empowerment, to avoid the golden cage problem, right?
Yeah, so much of what I said assumed that we know what the agent is, where it stops when it begins, where the world building begins and where the world ends. So I did not discuss the boundaries of the agent. So I assumed, for example, I didn't talk, for example, about altruistic agents. You can do that. I think I have a slide there. Here's a slide. Looks complicated. It's not that bad, actually. Basically, you have an empowerment of the human, empowerment of the agent, empowerment of the human versus agent, and empowerment of the human through the agent, and so on. So here, the agent basically works as to maximize the empowerment of the human first and foremost. The boundaries are predefined. The question where the boundary is a very interesting one. I do note that Carl Friston, for example, is trying to do that with the Markov blankets. I do think that this is probably not enough. You need more structure or a sharper structure for that. I think Markov blankets capture too much. So the question what the good boundary is that should be chosen is a very difficult one to decide. Because you have to handle things like symbiosis and things like that, the absorption of mitochondria into the cell, things like that. The question is when do you accept that, okay, I'm giving up empowerment, but I'm getting something else for that. I would say this is a very complicated question, not answerable in 2 minutes. But everything I talked about today assumes the boundaries are understood. Awesome. It's a very good point, Nora. I'm happy to talk to you separately on that.
Sure. Issue. Yeah, I think PIBBSS generally does some agent boundaries kind of work, and so I see where she's coming from. All right, we have 4 more questions, lightning round. Nathaniel asks, is empowerment resource rational on its own? If not, is there work that studies how organisms might maximize empowerment while minimizing complexity, a la IB?
I see that I should have met you in person. It looks like we have lots of things to talk. Yes, you're completely right. It's not. You notice very well, it's not. Empowerment doesn't care at all about resources. It's very wasteful. Because it will create all the necessary action sequences it wants. You can impose a constraint on the action sequences. That is, we call that impoverished empowerment. It's work by Tom Anthony. It's probably the most that exists at this stage. And basically there we started concentrating not empowerment, because empowerment is just cut off at the capacity of the actions, where what we look there is what action sequences are particularly favorable, or what are the action sequences that impoverished empowerment wants to keep. And it turns out that they are quite meaningful. It turns out that they are what you would call dominant actions or expressive actions, not some action, but they are actions that you feel, yeah, this is a special type of action. For example, they will typically span the space, they typically move objects, they will typically do something that has a name in human language. So the resource rationality on the actions would do that. What we did not do is, there's a little bit more. There's, of course, the Umwelt paper by Philippe Cap-Dupuy, 2007, if I remember correctly. And he looked at, can I do relevant information with empowerment as a utility instead of normal utility? You can do that, and it works. I think this is the only work of that kind I know. So it's worth looking if there's something else to follow up there. So it's Philippe Cap-Dupuy. If you can't find it, drop me a mail, ask me just for that. But empowerment itself is not resource rational. If you want to make it resource rational, you have to think about how to do it so that it will actually, the landscape will keep its informativity. Because by normally, if you say I give you just 2 bits, then basically it will have empowerment of 2 bits everywhere. So what is it that it's telling you? The only interesting information we found is in the actions. Question is there something else?
All right. Stavros asks, do you think empowerment is instantiated many times in a given organism at multiple organizational levels?
Well, the one reason why we're interested in informational quantities is because they're universal. So once you discover the idea, you can use it at every level. And so the hypothesis would be, yes, in principle, that's what you do. Once you find it, there's no reason not to reuse the principle. Well, I'm always troubled by assumptions of naive evolutionary theory that evolution discovers all these things over and over and new things all the time. I do think that evolution doesn't discover many principles. It discovers a few really strong ones. They don't have to be orthogonal, but they have to be relatively universal, because finding a new principle is very, very difficult and very rare. But evolution clearly works. So my argument is, if empowerment is really an evolutionary principle, then I think it's used everywhere.
Stavros says, well said. All right. Sebastian asks, much of what you're saying reminds me of the enactivist theories of Francisco Varela and collaborators. Do you know of any work that draws this connection explicitly?
Well, to be honest, it's a, in German you would say it's ein weites Feld. It's a wide field. A very famous German quote, actually. I would say, clearly I try to project down everything onto information, right? And the reason I do that is because it's quantitative. You can make predictions, you can make expressions, you get constructive quantities. And of course, it's certainly not the only way to do that, right? So I'm sure there are different ways to do it. And now we start seeing that dynamical systems theory seems to have, I mean, it was always clear that it's related to information, but only now we see how closely it is related. So I wouldn't be surprised if coming years we'll actually see more and more of such links. But the cool thing about information is, in my opinion, what it gives you extra, it gives you a quantification. And what problem with dynamical systems is that it's continuous. You can make all kinds of dynamical systems with all kinds of properties. And all of them may be computing the same things. So I feel that information is probably a better way to see what is it actually doing, what is the essence of what it is. I think I'm quoting Hannibal Lecter here, but what is its essence, right? So the point is, what we're trying to do is getting the quantitative essence of what a flow is and what the interaction with the environment is. But information theory is also humbling, because it tells you sometimes you don't understand it. It gives you answers you don't expect. It gives you, I mean, classic example is the information decomposition. Really, people thought, oh yeah, let's just do that. Information says, nope, I'm not going to make it too easy for you, right? And then you sit there and think, okay, it told me something I didn't know. And that's a good theory. A good theory tells you things you don't know. A bad theory is, or a mediocre theory is one that just answers the questions exactly as you ask them. That's not giving you much. So information theory, I like it because it tells me more than I thought about. Nice. Sorry for a very vague answer, but I hope I kind of got you a starting point here.
Oh, yeah, I think so. We'll see. Sebastian can write in the chat. Last question, if you don't mind going a few minutes overboard, from Mateusz. How does Jung's motto fit into evolutionary lineages that dramatically reduce their sensation or action channels over time? So from more complex mollusks to oysters, mussels to free-flowing chordates to sea squirts. So gradually decreasing usefulness value of sensory action channels over a time.
Yes, of course. That's an excellent question, and I'm happy that you asked, because I think it clarifies what we are saying, right? So as I said, all the empowerment examples we had were given a sensory motor equipment. Once you have that, you of course want to make it useful. When you evolve it, then you can make it more useful. We have actually a sense evolution. I think I have sense evolution somewhere here. I have the picture. Yes, yeah, I don't go into detail, but this is a sense of evolution scenario where we evolve actually the sensors, given a certain scenario, without going into but these are the results of the evolution. Evolution has very strong forming pressures when empowerment is maximized. However, of course, empowerment is not the only constraint that you are faced with. Constraint is your niche, constraint is energy, constraint is space. In sensor evolution, for example, constraints can be how many cells can you fit in the eye. Heat production is a big problem, by the way. Heat, you have to remove heat from your sensor. So if you have an infrared sense, that infrared sense must be able to remove heat from infrared detectors. So these constraints play a role. And of course, we have ignored them intentionally. So I didn't want these constraints to understand what empowerment does. But once you introduce the constraints, it may be actually better to have actuators and sensors match. As I said at the beginning, they have to match. And if you have them already, then you better go into states where they do match. But if you evolve them, well, there's not really a reason to make them bigger if your niche is fine, right? There's also another phenomenon that I didn't talk about it, that's piggyback information, where there are situations where you may get bigger sensors that you want. So it's a bit like buying, you want a phone, a smartphone to talk to your friends, and then the smartphone can do this and this, this and this, and you start doing it, and then your whole niche changes due to that. On the other hand, you could also have a situation where so much cost is involved, where it's really not getting you anything. Having this empowerment, it doesn't actually improve your survival. So when you degenerate your sensor, degenerate your actuators, it doesn't cost you, and then empowerment of course is irrelevant. So let's say empowerment is, of course, if you are an oyster, you have limited ability to, for example, compensate for a catastrophe of a global scale. So let's take an example. I have actually a historical example. Let's take China, 1421 was it? They had a huge fleet by which they started to explore the world and started to move also to America. I don't know whether they reached America, but they were a huge fleet. And then for some internal reasons, they decided, no, we get rid of this fleet and we just become a pure land power. And so they reduced empowerment. And that was a decision, and that worked for them for a while. But of course, the result was that the European powers later overwhelmed them. So in other words, when you reduce empowerment, it means also you put yourself at the mercy of your environment. So locally, that is maybe perfectly a reasonable balance between your resources. On the long run, that's probably not. Humans that can deflect a meteorite, an asteroid from Earth, definitely have an advantage over the dinosaurs. And I do think that perhaps a bacterium doesn't care too much, but if you're anything along the higher living organism, I think giving up on empowerment is not necessarily a good idea on the long run.
All right. And if you'll spare one more, Rui does seem to have spent a lot of time typing it up, and I think it's interesting. In biology and neuroscience, essentially exploration and exploitation are kind of the two sides. I assume you know what they are, and so empowerment seems to fit exploration, but it leaves out exploitation. If true, is it not insufficient to describe organisms as acting based on empowerment?
Okay, so this is a good point. First of all, empowerment is not about exploration. This is a misunderstanding, actually. It's not about exploration. It can be misused for exploration, and it sometimes works, as I said, in the epistemic level, for example. And it's not entirely not about exploitation. So it sits somewhere in between these two. Because empowerment is actually about exploitation. I mean, if you have something that you can do, you can exploit things. As I said, you can take empowerment and turn it into value, into actual value. And I do agree, like with the football example, the decision when do you move from empowerment to actual value, so where you take empowerment as a voucher. Empowerment is a voucher. You put the voucher down and you get food, or you get a mate, or you get a goal, or you could do something that you want. That's when the exploitation happens. And this is not a well understood thing when this exchange happens. It's even worse than that. If you look at football, I like football as an example because it has the right level of complexity. So you have this team and you can say, I control the ball. And if you control the ball 100% of the time, that's it, good. But it's still not winning you the game. You still have to make the ball move towards the opponent goal. So you can say most of the game, it's mostly empowerment with a tinge of moving towards goal until you can make the transition from strategy to tactics, where, okay, I see my partner in front of the goal, now it's tactics, and I'm just planning 1-2 steps. So this transition and this tendency, this drift, it's not well understood. It's an open question how to do that. So I definitely don't claim that empowerment is the whole story. What I'm saying is that it is a good candidate for a generic, robust guidance when you don't know what to do. Once you know what to do, yes, that's what you should do. You should do what you know to do, right? But it is not, this theory does not tell you also when to make the transition from this potential to the commitment. But I would say it's neither exploitation nor exploration, somewhere in between. So it's more like a quantum superposition of the two concepts.
Yeah, makes sense. All right. Thank you so much, Daniel, for answering 17 questions during this talk. Thank you, everyone, for coming to see this. We'll have a upload of this video, hopefully on YouTube sometime in the next few weeks. And yeah, welcome to come to our future talks. Thank you again, Daniel.
Thank you for the invitation. It was a pleasure. I would have liked to see you in person, but this is the second best thing. Thank you very much.
There will be time, I'm sure.